Hello, everyone. We are the Metallurgy Mob from the University of New Haven, and this is our everyday multi-tool project. This is our submission for the 2026 Additive and Steel competition brought to you by America Makes. So here's our initial design and drawing. We drew a lot of inspiration from Swiss Army knives and these above designs where the hammer is built into the frame of the multi-tool. And we wanted to do that just to reduce the amount of stress that might be on the pin if we were to make the hammer movable. Here's our final submission in SOLIDWORKS. You'll notice that the hammerhead is one piece with the rest of the frame of the multi-tool. The glass breaker is on the back of the hammerhead, and there are also some hex sockets on the head of the hammer. One side is imperial sized, and the other side is metric sized. So as far as the folding out tools, there are the wire cutters on the pin closest to the hammerhead. Also on that same pin is a combination of a number 2 Phillips head and a hex key. On the other pin, farthest from the head, is a 3-in-1 flathead screwdriver, seatbelt cutter, and bottle opener. Also on that far pin is the socket extension. So if you need any more socket sizes or whatever attachments, you can put that there.
So this is our design. We decided to 3D print this on a desktop 3D printer out of PLA plastic. We printed it in the orientation you see on the left. On the right, you can see the fit in the hand, and we're very happy with this. And you can see that all the features, such as the sockets and the glass breaker and the hammer head, all came out how we wanted them. So we realized very early on in the project that the 3D printer at our school would not be big enough to print our whole part. So we contacted University of Texas, El Paso, to contract the 3D printing of this part. The machine they used was a EOS M290, and they chose the layer height of 40 microns. You can see the orientation of the part is kind of at this, diagonal formation, and this is to reduce shrinkage and increase strength overall. So when we got the part in the mail, it came in looking like the top left picture. Notice all the support material and the overall orientation of it. The picture on the right shows the other side. Notice the really good finish on the part. And the bottom left picture showcases the tools, not in the handle, just laying on the workbench.
Here's our finalized multi-tool after our post-processing stage. During the stage, the supports were removed and each part was cleaned up using files, sandpaper, and other items. Each individual tool piece fits within the handle of the hammer, and each is secured by M4 screws, locked by a matching nut on the opposite side of the handle, and held in place by washers in the middle of the handle itself. The scissors use a copper wire riveted to become a pin so that the blades can open and close with user input. And lastly, the overall base of the multi-tool was smoothened to provide a more ergonomic grip during use. In addition to making the tool, our team performed an electron backscatter diffraction analysis, which sends electrons onto a sample piece to see the surface grain structure. Samples of SS316 steel were tested in raw and 3D printed versions. The 3D print sample was made using our university printer, utilizing a stripped infill pattern with a laser power of 215 watts and a speed of 930 millimeters per second. The 3D printed version provided a strong columnar grain structure along with the print lines, whereas the raw sample had a more uniform all-around strong structure. Now, our team would like to display the capabilities of our multi-tool.
Okay. Process.
And show it.